question is how do you create such a large cross section in a system where the velocity is going to be fairly low, of order 10 kilometers per second? So I am 100% agnostic on how you might create such a model from sort of a model building standpoint. So it's just a statement that if you have a model that has a self-scattering cross-section as large as 50 centimeters squared per gram, that's not obviously ruled out by any astrophysical constraint that I'm aware of on the scale of dwarf galaxies. Something I should clarify, though, is that there are fairly robust constraints on the scales of galaxy clusters, and I didn't talk about that at all. Those constraints actually do not come from the Bullock cluster, contrary to popular belief. The strongest constraints on self-interacting dark matter actually just come from the central densities of galaxy clusters. So the central densities of galaxy clusters in dark matter are high enough that if you put in a cross-section of order unity, you just cannot achieve densities in dark matter as high as that are observed, independent of any colliding clusters or anything like that. So a 50 centimeter per square per gram cross-section on the velocity scale of galaxy clusters is definitely ruled out. You couldn't make it. That is not viable.
Is it possible to use the solution to know the cross-section of the self-interacting dark matter? For example, this one, 50 and 10, they are like basically the same, right? And let's say if we see a core with the size roughly 1 kilowatt second, can we say that that thing has large cross-section? Or
there is, so based on the simulations we've run so far on the scale of dwarf galaxies, there's a pretty big degeneracy on the core sizes that you get for cross sections between about 5 centimeters squared per gram and 10 centimeters squared per gram. So as far as I know right now, it's actually difficult to distinguish the two. However, my guess is if you had enough statistics, well, we haven't run that many simulations, my guess is there would be some differences, but the differences, I mean, it would be small.
If I may add a comment, I think if the question was, yes, okay. If the question was how could you reach a cross-section of 50 centimeters squared per gram, actually you can do that very easily within a particle physics model. Models that have light mediators, the cross-section scales as 1 over v to some power. So if you have a Rutherford scattering, it scales as 1 over v to the 4 if you have a massless mediator. So actually having low velocities, you get large cross-sections. So you can easily achieve this cross-section in particle physics models.
There was a comment here, and I would like you to clarify this. Why the sphericity of clusters is not any longer used? It was an argument that was given.
Yeah.
And
so I mean, right. So there is a constraint based on the sphericity of galaxies and galaxy clusters, and this is a point that was, I think, made first by Jordi Moralda-Escude in like 2002, I think. And it is generally true that if you run a dark matter only simulation in self-interacting dark matter, you get a region in 3D in the centers of these galaxies that is spherical. And that's because you have this sort of, the system becomes isotropic because of this scattering. Two things happen to make that constraint. It's still an interesting constraint to look at, but it's not as powerful as people first thought. So one is, of course, that when you're doing a lensing constraint on a cluster, on the shape of a galaxy cluster, that's a projected constraint. And so these halos are still fairly aspherical at large radii, and you're getting a projected shape constraint. And so that lessens the constraint. But also, we now realize that when you actually grow a galaxy in the center of a self-interacting dark matter halo, that self-interacting dark matter actually conforms to the shape of that baryonic potential. So there's a crosstalk between the baryonic potential and the SIDM where they kind of conform to each other. And one way to think about it is you have an isotropic, sort of what's imposed by SIDM is an isotropic velocity ellipsoid. So the z velocity dispersion is the same as the xy velocity dispersion. But if you grow a flattened potential, then you can have a stronger restoring force in the z direction. But the velocity dispersion is the same. So the only way that can happen is if the thing kind of flattens out a bit. And so you actually have SIDM is more responsive to the baryon potential than the CDM is. And you actually get very flattened structures in SIDM once you account for the baryons than you would naively think. In fact, it can be more flattened than the CDM. And that makes these constraints really complicated, and you have to start including baryon structure. So that's why that's less, people don't look at it as much as they used to.
Other questions? Other questions?
In regard to the type of stripping stuff of subhalos, does that depend on the mass of the halo, or is it just the structure?
That's a great, because the question is, in this tidal stripping that you get, can I see them? Sure. I made it turn it on. That's not on. There we go. So the question is, in the tidal stripping that you get from these subhalos.
Repeat the question.
Yeah, so the question is, the tidal stripping that you get from these subhalos, is there mass dependence? So like, if you have, is there a certain subhalo mass regime where they get more destroyed than others? And that's a great question. We have looked to see if there's a mass trend in our simulations, and we don't see any strong trends. So as far as we can tell, it affects big subhalos the same way it affects small subhalos. There's no obvious trend. But it's kind of hard to tell because there aren't as many big subhalos. So the statistics are worse, and we only have a handful of simulations that we run. But once you go to sort of smaller than about 10 to the 8 solar masses, we don't see any real trend. You might have thought there could have been an issue with like dynamical friction or something, but we just don't see it.
So when the self-interaction, self-capturing cross-section has some velocity dependence, what happens? I mean, for example, when it has like 1/v dependence, how does it affect
So, okay, so the way to think about it is that, so there's some velocity dependence. If you're looking at a galaxy cluster,
Can you repeat the question?
yeah, sorry, the question is, you generically expect these self-interacting dark matter models to have a velocity dependence, like for example, 1/v to the 4th or something. So you might then expect there to be a smaller cross-section at high velocity and a larger cross-section at low velocity to some point before it flattens out. So basically what you find, right, is if you're studying galaxy clusters, right, and you might want to make a constraint on the cross-section using a galaxy cluster. Well, in a galaxy cluster, the velocity dispersion of the dark matter is like 1,000 kilometers per second. So what you care about is what's the value of the cross-section at 1,000 kilometers per second when you're looking at a galaxy cluster. And we know from cluster densities that the cross-section probably has to be smaller than about 0.1 centimeters squared per gram at 1,000 kilometers per second. Now, if you want to solve the small scale problems at dwarf galaxy scales at 10 kilometers per second, you want to have a cross-section that's of order unity there. But that's for velocities of 10. So you want something that has a cross-section of order unity, maybe 10 at velocity dispersion of 10, and you want to have something that has a cross-section smaller than 0.1 at a velocity dispersion of 1,000. And that's kind of where things are now. So it could be much lower than 0.1 at a velocity scale of 1,000, and that would be fine. So I think the way to think about it is that way, that it depends on what laboratory you're using. So if you're using a galaxy cluster, you're probing dark matter physics at 1,000 kilometers per second. If you're using the Milky Way, it's 100 kilometers per second. If you're using a dwarf, it's 10 kilometers per second. So you think of it as these like different laboratories to kind of map out behavior at different velocity scales.
So what I imagine is that if we have a region close to the halo center, what I imagine is that the typical velocity of the dark matter particle is maybe larger than the outer region of the halo. So maybe that could affect somehow affect the
Yeah, so the question is, well, but it's not true that the velocities are exactly the same at all radii of the halo, so this can matter. And that's true. You're right. So in detail, it's not quite right. To first order, dark matter halos are isothermal, give or take. So they're not that much different, but you're right, sort of factors of 2. You can get different velocities at high. One reason why it doesn't matter that much is that in the outer part of the halo where things are a little colder, there's no interactions anyway because the densities are really low. So the only place you really see effects is at the core. And at the core of the system is basically isothermal in SIDM. And it basically has velocity dispersion set by Vmax of the halo. So it's these effects in principle are there, but they're not first order effects. They're like probably second order things.
This is Ferdinand. So you meant basically the weakest constraints right now are like from 1 to 100 solar masses for the primordial black holes. Where do we expect kind of the strongest constraints to come in the next 10 years in that region? Like what telescopes or what data do you think will kind of...
Can you repeat?
Okay, so the question is the constraints on primordial black holes in roughly solar mass region are weakest between 1 and 100 solar masses at the moment, and what's expected in the future for improved constraints. So, I mean, actually, if the supernovae lensing things are reliable, that's already a reasonably tight constraint in that region, as in it's independent of mass. Ditto the quasar microlensing. If people actually went as far as calculating a constraint on compact objects, the halo fraction, that certainly will be a constraint much less than 1. And once you've got a constraint much less than 1, you're then squeezing down. But I did mention on one of my slides a couple of other possibilities, and that's lensing of fast radio bursts and also pulsar timing arrays. And so if you have, I can't remember details beyond what I put on my slides off the top of my head, but there were references there if you're interested to go and look at.
But those are expected to improve in the next few years, or you are
I think longer term in the next few years.
longer, like 5 years, 10 years,
Yeah.
or something like that. Are people really going to look more for this black hole limits and so on? Now there seems to be, but observationally, I mean, in theory, it seems yes that there is a lot of interest. But I mean, observationally, are people, some people who do actual, astrophysical observations going to this area to test this idea, or this is too weird for
I think
astrophysicists?
it would be nice to firm up, so the question was whether people are really, from an astrophysical point of view,
Yes,
still
sort of.
interested. And it would be nice to close some of the wiggle room in that solar mass, tens of solar mass regions, as in there are astrophysical uncertainties. It would be really nice to firm things up. Well, maybe there's no interest in pressing constraints down by an order of magnitude. It would be nice to have things that were completely watertight and don't rely on assumptions. That's the solar mass region. If you did actually want the dark matter to be black holes, probably the more promising region is downwards. So that would be the one which would be more interesting to look at.
Which one?
Oh, so going to, exact numbers I can't quite remember, but about 10 to the 18 grams. So you get just above the gamma ray limits, but below all the microlensing limits. So this is this region where there are...
This is where you had delta function, one of the delta
Exactly,
functions.
yeah. So, and this is the region where there are possible constraints from neutron stars and white dwarfs, but those are possibly not so robust. So there's more room for manoeuvre down there, and maybe it'd be interesting for somebody to come up with some good ideas for constraining that sort of mass. I guess it's difficult because they're so small, but yeah.
Moreover, is there any model that can give you a very narrow sort of delta function like mass function for, because all the features or mechanisms tend to give you a certain spread in mass, right? I don't know if there is any mechanism that can give you a feature like this, a very sharp, delta function.
So in terms of the collapse of large density perturbations, the critical collapse phenomenon means you get a spread of a few, however sharp your feature in the power spectrum is. I mean, that's fairly close to delta function-like. Otherwise, I guess you'd want a completely different mechanism. I don't know.
So for black hole masses that are quite a bit bigger than one solar mass, like 10 to the 4, 10 to the 5 solar masses, where do those constraints come from?
So the question is, where do the constraints on more massive black holes, so 10 to the 4, 10 to the 5 solar masses? So that's a region where I think the CMB constraints are actually fairly reliable, as in you get sort of accretion onto the black holes and then radiation, which would mess up the CMB. There are also dynamical constraints, in particular from disk heating, which is something that got talked about in another context this afternoon. But if you had 10 to the 5, 10 to the 6 solar mass lumps of dark matter flying around, they would undoubtedly heat up the disk.
And it doesn't care about what forms the black holes, right? It could be any black hole.
Exactly, it's a pure dynamical thing, yeah.
So it doesn't matter that, in this case, it doesn't matter that it's a black hole, it could be a lump of anything that would be so big with poke holes in.
Well, I guess things that are big enough that they're similar properties to dark matter, canonical cold dark matter substructures, they're much fluffier and diffuse, so they don't have that effect. It's very compact things that will cause the problems.
Things like Gaia, very astrometric, very precise, close by astrometric measurements can do something for substructure or for black holes or substructure of some sort. I'm not sure. So, whatever.
I mean, I think Gaia,
Because you could.
right. So I think in principle, Gaia, like if you have proper motions for the stars in these streams, people have talked about, if you really map out the 3D velocity structure of these streams, you can start constraining how often stuff is punched through. And I assume that this is probably a really strong constraint on these, like, if they weren't ruled out already, these like 10 to the 5 solar mass primordial black holes, because they would just tear the heck out of these streams. And certainly the substructure would do it too. And I think also proper motions could be really important for this wide binary constraints. I don't know whether or not Gaia can get to the dwarfs with enough stars, but I know people have talked about, detailed studies, looking for wide binaries with the next generation of, missions, like WFIRST even. I have a naive question about primordial black holes. So these constraints from wide binaries, I was thinking about the Oort cloud. So like you have this like giant, all these like extended low mass things orbiting around the sun that are like way out, like maybe even a light year out from the sun.
This is the asteroid belt?
Well, no, it's way out, way farther than the asteroid belt, way out, like way out there.
Ah, so outside the planets.
Yeah, way outside the planets, there's all these rocks basically that orbit around. And I was wondering whether, like, if these primordial black holes are flying by, whether they would make comets rain in on the solar system or disrupt the Oort cloud. And if people, if anyone's like looked at this kind of stuff.
I've got a dim memory of somebody having looked at this in the context of WIMP microhalos,
Okay.
as in the Earth mass.
Yeah,
so
yeah.
they do that, but I don't know if anybody's looked at it.
Seems like primordial black
Well, of
holes would
course
do
you have
more
to say-
damage,
no,
right?
exactly,
Yeah, make it
so-
worse.
So that's certainly worth looking into, I think.
Okay. That might be fun.
Yeah, so when I look at the movie about the satellite galaxies, so most satellite galaxy is located in the nearby these galaxies, but I saw some satellite galaxy like L1 or 2 detected by IDSS.
Yeah.
So my question is that does have any physics meaning here because it's very few the
Yes.
same instrument, same technique.
Yes, right. So the question is, you notice that if you look at the discovery of all the new dwarf galaxies, most of them are pretty nearby, like within 50 kiloparsecs. But there are a few of them that have been discovered by Sloan that are like out at 100 or 200 kiloparsecs. Does that have any physical meaning, and why is that?
Yeah.
So it's basically what you're seeing is a selection effect, that the faintest galaxies can only be seen nearby, and there are more faint galaxies than bright galaxies. So you can only see the faint ones nearby, so you're going to see lots of faint galaxies nearby, and you only see the bright galaxies far away, and there aren't as many bright galaxies. And so you don't find as many galaxies far away just because you can only see the bright ones. So we expect that there are probably hundreds of faint galaxies far away, like at a few hundred kiloparsecs. But so far we've only detected the ones within 50. But there probably aren't that many more bright ones far away because we would have seen them already. That make that? Yeah.
So you touched on this a little bit earlier, but I was wondering if you could say anything more. So with these warm dark matter candidates, you can also have quite non-thermal distributions that don't have a kind of a single temperature as like a good description. So you touched on this a little bit further, stellar neutrinos, but in general, do you expect to see, for some more complicated thermal distribution, effects on the substructure?
Yeah, so that's a great. So the question is, imagine you have a dark matter model that it has a velocity. The particles have a velocity distribution that's non-thermal and some complicated velocity distribution. Do you expect to see effects of that on the substructure and other things? So it depends, and I don't think these have been fully explored, but for example, we wrote a paper with Louis Strigari many years ago where we looked at models that had really kind of weird non-thermal velocity distributions. And we were able to write down models that basically had power spectra that looked like pretty normal-ish thermal warm dark matter, but they had much lower phase space, primordial phase space densities. That is and you actually saw phase space created cores in the middle of halos that were observable. So a real like Liouville theorem like phase space limits that created cores. So there are models you can play with where if you really allow freedom in the velocity structure, you can create power spectra that are sort of CDM-like, but with primordial phase space densities that actually create observable structure in the middle of dark matter halos. So that's one thing you could look at and kind of play with. But in terms of sort of the way the power spectrum rolls off, I think, like I said, I think that's harder. There might be things you could see at high redshift in the marginally nonlinear regime where you might actually start seeing things. But I think in the highly nonlinear substructure regime, it's kind of like all or nothing kind of stuff. Like as soon as you fall off by a factor of 2 in the power, it just starts, those halos start getting destroyed and you don't see it. At least that's what I think right now.
Another question, when you simulation, so how do you know that the result can show a problem on core or too big to tell or galaxy satellite? And when you constrain with the observational data, there are a lot of, a bunch of data. How can you figure out what kind of data or what kind of galaxy? How can you figure out how to constrain and how to compare with the observational?
Yeah, I think I understand the question. Correct me if I'm wrong, but I think the question is there's so many different constraints that you're worried about, like cusp core, too big to fail, all these other things. How do you decide which data you're using to constrain your models?
Right, that's the one. And the one is the value simulation. And how did you know, the example of simulation on shell interacting dark matter, how did you know it can be shown for core problem or too big to tell?
Oh yeah, okay, so how did we know to run a certain self-interacting dark matter model to constrain cusp core, too big to fail or whatever?
Right.
I mean, I think to begin with we didn't know. So we actually thought, so I personally thought we were going to rule out all this nonsense about self-interacting dark matter the first time we ran the simulations because I thought we were going to just not have densities high enough. We weren't going to match any of the data. They're going to put this stuff to bed and then move on to CDM, and that's not what we found. So I think we didn't know. I think there's a lot of surprises and intuition you gain from running cold dark matter simulations that just does not translate to self-interacting dark matter. And it was a very slow process. You know, like a lot of people thought you're going to erase substructure. Well, you don't. A lot of people thought that the shape constraint was going to be a big deal, where it turned out it wasn't. And so the main thing that survived and is very robust is you do make cores in your dark matter halos. And that helps solve cusp core, and it helps solve too big to fail. So, yeah.
Another question is,
I don't know if anybody else has a question.
I have a question on self-interacting dark matter. So I was wondering whether sort of the more detailed particle physics of a particular model may affect the effect of self-interacting dark matter. So besides the velocity dependence, in some models you naturally, let's say reasonable models, you have, for example, multi-component dark matter. And in this case, maybe I should start by saying that in the simplest models, you have one kind of particles, and the momentum transfer is determined by the mass, which also is the mass of, well, it's the mass of dark matter. But if you have multi-component dark matter, then you can have smaller, more frequent scatterings of larger, more frequent scatterings of smaller momentum transfer.
Yes.
Would you expect this to have an effect?
I don't know. I mean, I think that's a great question. So the question, yeah, I guess your mic, so I don't have to repeat. I think that's a great question. I mean, I think you would have, the constraints would be entirely different, right? Because they would not be just on the cross-section. They'd be per unit mass. It would be some more complicated thing that depended on the fraction of the dark matter that was in the form of this. And is the idea too that if you have two flavors of dark matter, they scatter off of each other with one cross-section and scatter off?
Right,
like,
so if you just had two different kinds of particles and they just, each one of them interacted with its own kind,
yes,
then that wouldn't matter, because you would say, well,
yes,
the lightest one doesn't matter, it doesn't make up very much of the mass of the matter in the galaxy, so fine. But then when they scatter with each other, then what happens is that the cross-section for this scattering is usually in the non-relativistic regime determined by the reduced mass, so the lightest.
yes.
So the cross-section is large because it goes as 1 over the reduced mass squared. But also the momentum transfer, so these scatterings are more frequent than the heaviest particles with each other.
Yeah.
But the momentum transfer is smaller because the momentum transfer is also the reduced mass times the relative velocity.
Yes.
So it is. So should one take these scatterings into account when one is trying to estimate roughly the effect before going to simulations, I guess?
Yeah, I mean, I think so. I mean, I think the question is.
So what would be the quantity that matters, I guess? That's the...
I don't know. I think I would have to think about it offline a little bit, write it down. But I think that it's a little bit complicated because the light... I don't know. It's complicated enough that I can't answer. I mean, what I found is that every time I think I make a guess of what's going to happen with SIDM, I'm wrong. So I don't want to answer the question. But I think it's something we should look at, especially if it's well motivated. It might be fun to simulate, and I think we can do that. Because we have it coded up now where we can turn on multiple types of particles, and some of them have one cross-section, some have another, and I think it's possible we could probably simulate it. So if it's well motivated, it might be worth just doing a couple toy models and check it out.
Okay.
So. And
perhaps a related question. If you then have multi-component dark matter and frequent enough scattering so that you get sort of an isothermal situation, So would you then expect the different components to have different velocities if the masses are different? Is that?
Yeah, I guess what you conserve is the kinetic energy will be isothermal, but so mv squared would be constant. I guess it would be like an ideal gas of different, yeah, so the heavy particles would move a little slower than the light particles, right? So then they would sink. Yeah, that's kind of interesting. That'd be kind of an interesting model. The heavy ones would kind of sink.
With some like segregation, there would be a
Yeah.
segregation mechanism.
Yeah. Huh.
So, but typically this multiple dark matter possibilities have not been studied, right? There are no simulations of multiple.
No, a lot of people have asked me about that.
Multi-component dark matter.
Not that I'm aware of.
There are so many different possibilities.
It would be fun to do it. I mean, for sure. I think it'd be fun to look at.
Maybe it would be fun also to classify them in some way, in which so that you get some representative, because there are several different type of effects that can happen, right?
Yeah.
But there have been no simulations for mixed dark matter models either, right? Even just cold and warm.
No, there have been cold plus warm. And there definitely were cold plus hot a long time ago. I'm pretty sure there's been cold plus warm simulations. Typically what you find is the cold dark matter dominate, basically you get cuspy halos, and the warm dark matter kind of lives at the outer part of the halos and in between, and the cold dark matter still makes a cusp with overall less density. If that's all you do, then that has.
Those are constrained more than cold dark matter alone. I don't know. I mean, I haven't seen.
You see little features in the power spectrum, because the warm piece drops out, so you see a little dip there at small scales, and then the structure of individual halos looks kind of like CDM because that kind of the CDM dominates the halo. Yeah.
There is a question here and there, here and then two. Yes.
Oh, I just wanted to follow up with Kalia and ask what you thought, if you could tell us more. I don't know if this is a fair question, but if you could tell us more about some of the multi-component dark matter models that you actually thought were the best movie.
Yeah, so I tried to talk a little bit about that in the lectures. So for example, multi-component dark matter models occur very frequently when you have asymmetric dark matter coupled to light mediators. And the reason for that is, it depends exactly on the model what the reason is. But so one of the simplest models is atomic dark matter, which I sort of showed. So if you have asymmetric dark matter that couples to a gauge vector boson, then by gauge invariance, you don't want to have, by gauge invariance, you have electric charge neutrality, dark electric charge neutrality, and therefore you need two species, like with ordinary matter, right? And these two species will interact with each other. So it is something that you didn't ask for it, but by assuming that you have asymmetric dark matter and coupling to a light mediator, you derived it, right? You deduced it. Now, why is asymmetric dark matter interesting? In the context of self-interacting dark matter, it is interesting because asymmetric dark matter allows large couplings to light mediators, more so than symmetric dark matter, right? Because with symmetric dark matter, you don't want to annihilate it too much. So the same coupling that gives you the self-interaction also gives you a contribution to the annihilation cross-section, right? So if you care about having a consistent sort of cosmological description from the beginning to the end, then asymmetric dark matter is a natural host for self-interacting dark matter. So this is one example. You get atomic dark matter, so you get both ions and atoms, and it depends on which part of the parameter space you are, but even if you don't get atoms, you already have two kinds of ions. And then you can entertain other possibilities, more complicated gauge interactions, and then you can get even nuclear physics and things like that. So.
I guess to follow up, I think yesterday you is there any reason to think from a theoretical point of view that you would have like wildly different masses necessarily?
I think, yeah, so if you have, so the question is, if you have an atomic dark matter model, whether, what would you expect the masses of the dark proton and the dark electron to be similar or different? I would say that in order for them to be the same, you need a symmetry. So you need a reason for them to be the same. And there are some models which have this additional structure, but in general, you do not necessarily have this structure.
Yeah, so one will be lighter than the other just because there is much more.
I have a naive question. So like, is it interesting or any kind of clue that the cross sections we need to make SIDM do interesting things isn't that much different than like nucleon scattering? Like, is that a clue or is that just?
It is, and I mean, if you want to, it is very interesting, certainly, because then you can put it together with the fact that you have similar densities of ordinary matter and dark matter, and okay, you want similar cross sections, and then back in the time when DAMA was more
Yeah.
of a possibility, then that also. So it is interesting, but yeah. So.
Just at that level, like, what do you do with it? Yeah, okay.
So there was another,
I have a question.
yeah.
So in the CDM scenario, can the baryon feedbacks alleviate the two-bit problem?
Please do repeat the question.
So the question is, within the CDM scenario, can baryon feedback alleviate the too big to fail problem? I think the answer is yes, it can alleviate the too big to fail problem. Whether or not it can solve the too big to fail problem, I think is still not settled. I think the too big to fail problem around the Milky Way can be alleviated by a combination of stellar feedback and also this disruption that I talked about, this enhanced disruption. That goes a long way. The question I think is more problematic is this issue of the field. Like the fact that you really do, it does sort of seem like there are these big halos, just you don't see enough dense halos in the field. Feedback doesn't seem like it's strong enough to lower the densities of the lowest mass galaxies. But it's possible that feedback could do it. I think the jury's still out on that.
And what about in the local group, not in the galaxy, in the local group?
So it's possible in the local group that feedback can do it because there is a little bit of enhanced stripping that you get even in the outskirts. We have a paper right now we're working on that's like local group fire simulations that it looks like the problem is definitely alleviated. Whether or not it's solved, I'm not quite sure, but it definitely it helps. More than I would have thought a couple years ago, for sure.
It seems like if the diameter is made by 20% warm diameter, 80% cold diameter, and if we include a baryon feedback, then we can solve all the three issues.
I think that's probably true. Like if you have if you have a major component of warm dark matter, it starts helping a lot.
Okay.
Yeah.
So you have your dark matter model now. Yeah. 20% cold, 20% warm, and you're done.
Yeah, I mean, feedback does stuff. There's no doubt about it. I mean, it really does. So.
There was here another question. You had a question? Or somebody, I don't know, you don't.
Maybe can I have?
Yes, I think so. Yeah. Or anybody else, if anybody else wants to. No? There are people who never talk. That was my idea. Everybody would talk. We don't have discuss enough that you will have a clear, huge amount of questions to ask. So everybody.
So I have a question. So in the title strip, you mentioned that many of the halo orbits are will get close to the core at one point. I'm just curious, is this related to any physical reason, or is this a pure coincidence?
Well, okay, so the question is, a lot of the subhalos get close to the core of the halo. Is this a coincidence, or is this a physical reason? Like, why is this? I mean, I think the basic reason is that dark matter halos form from some initial overdensity that expands with the universe. At some point, it stops expanding and then recollapses. So the central region recollapses, and then the next stuff recollapses. As the system is expanding, it's fragmenting into little halos. And those little halos are the things that fall back in. So they just are falling in on fairly radial orbits, because basically in the first case, the simplest scenario, it's spherical collapse, and stuff just expands radially and collapses back in radially. In detail, that's not what happens. It's not exactly spherical. It gets torqued up from the large-scale structure. It comes in with a little bit of angular momentum. But broadly speaking, dark matter particles are on pretty radial orbits, and the substructure is also on pretty radial orbits. And it just has to do with the nature of gravitational collapse in an expanding universe.
Any other questions?
I have a naive question about the simulation. And so currently in the simulation that we simulated dark matter and baryon particles, let's say at a mass scale 10 to 3, several thousand solar mass over a very large radius. So and I think that this is mainly restricted by the computational power we have. So let's say in the future we have sufficient computational power, and then we can reduce this mass to a reasonable smaller one, and then reduce this scale. And then what's new we can expect except the resolution?
Oh, so the question is, as we go to higher and higher resolution in the simulations, what new can we expect? Like, what's going to change in these simulations? Well, I mean, at some level, it's going to get harder. Because when you start resolving, when you start having masses per particle that are smaller than some stars, right? So we're getting to the point now where you have baryon masses that are 30 solar masses in some of these simulations. There are stars bigger than that, right? We know there are black holes of that size. So then you have to start doing things like, you can't just sample a random IMF because your star particle is bigger than an individual star. So you have to start thinking hard about just how you subsample the IMF. Like, how is it that you're going to turn that gas particle into stars? So you start doing things like that, so that you have to rethink about how you do things. And of course, the people doing first star simulations are already working on those issues. So you're going to start seeing, I think, bringing together the kind of simulations where people are actually trying to simulate the first stars, where they're doing all that complex chemistry and they're actually collapsing, fragmenting structures that really have things that are close to stellar nuclei that are just about to ignite as fusion is about to turn on, then they'd stop their simulations. You'll start having to do that in a cosmological simulation. And who knows what we're going to see, right? Because you could self-consistently start calculating ab initio, like initial mass function of collapsed objects. That's going to come out of your simulation. So things like that and then you may get it wrong. Like, you might get an IMF that's just wrong, and then you got to rethink what you're doing. So as you go to higher resolution, you'll have to actually start getting the right answer on small scales and not being able to plug it in ab initio. So it'll be things like that. It'll be interesting to see what happens when we get to that scale. And then, there's always this issue of like, well, when does it become weather, and when when you start simulating at such high resolution, and then you're like spending all your time like simulating the details of some collapse of some complicated molecular cloud, and like, do you even care about that, right? So it's going to be interesting to see over the next 10 years as people start really being able to resolve the structure of individual molecular clouds, whether that just becomes a different subfield on its own and whether galaxy formation changes dramatically. I don't know, but it'll be interesting to see. I mean, we're at the cusp of that now. Well, it's kind of amazing, really.
I have a question about the reionization. Do any these models, these structure formation models, help with understanding what happens, what reionizes the universe? Because you put it by hand. But,
Right.
are there successful simulations of reionization, or you have to assume a lot of things so that you get?
So the question is, are there successful simulations of reionization, and do you have to assume things? There are pretty successful simulations of reionization. So there are groups that do full radiative processing, and they're actually trying to reionize the universe self-consistently within their simulations. This can be done. There is enough structure collapse at early times to, in principle, reionize the universe. It depends on, the big questions are, in principle, there are enough photons being created. The question is, are those photons absorbed by the gas as they're trying to get out of the galaxy so that they can then go out and reionize the universe? And so that's the issue. So that's sort of encapsulated into the escape fraction.
And this is all due to supernova explosions, or there are other things?
Well, the ionizing photons usually come from massive stars. But then supernova explosions then blow out bubbles in the galaxies that then can allow those ionizing photons to escape. And so it's kind of all complicated in those in that kind of stuff. But I mean, I would say that there are no obvious, given the caveat that we don't really understand how to calculate escape fractions of ionizing photons, if you allow large enough escape fractions, there's plenty of photons to do it.
So there's no problem.
There's no obvious problem, but I mean, then you get into the details. Well, okay, well, in many simulations, the escape fractions just aren't that high, and they don't get out, and you don't reionize the universe. Why not? And so there's issues like, well, sometimes when you have binary stars, you can start those high mass stars can live a little longer and then produce ionizing photons for a little bit longer, and that helps. So that it gets down to details like that, like how many binary massive stars do you have, and how does that affect things? Do you have runaway stars that you have some kick out, and then you have a high mass star that's kicked out, and now it doesn't get shielded anymore, and all its photons can go and contribute to your ionization? The other questions are, is it low mass galaxies that create reionization? It seems right now that you actually need that stellar mass function to go down pretty low masses to produce enough ionizing photons to reionize the universe. But that's kind of where we are now. I think most people don't think you need like a lot of AGN or mini AGN or anything like weird like that. It looks like just standard stars. You can do it. I think, again, this is where warm dark matter models might have a problem. So it might be difficult to reionize the universe early enough in warm dark matter models. You just don't have enough early structure. Yeah, yeah.